开始了啊，对，你去 check 一下，就跟刚刚那个，对，好，这样，
好，
播放。没有出来，哎，这个没开是吧？哎，那个怎么开？
我没有接，开个机。
哦，里面接的。有，没那么快，反应没。那个没有落，放着。
那个旁边的要。
不用了，那个就好了，没有多少人。等那么久。那个灯有亮吗？摄影机的有没有遥控器？啊，我看了。哦，有了，亮了。好。Okay. Last time we stopped here. Last time we're talking about multi-dimensional mesh. Okay. And if this multi-dimensional mesh, if every dimension they have same size, okay, then we call it d-dimensional K-array mesh. Okay. And if the K is binary, then it's a special K-array mesh. Okay. It's called hypercube. Okay. So a system of hypercube with n nodes, you have log n dimension. Okay, so and the construction of this hypercube, a high dimensional hypercube can be constructed by a low dimensional hypercube. For example, this zero dimensional hypercube is a single node. Okay, and it can be constructed. One dimensional hypercube will be two of these and connect the corresponding nodes. Okay, if you treat this as two zero-dimensional hypercube, okay, and the corresponding elements, okay, you correspond pair of elements, then you connect a pair together. Okay, then it becomes a one-dimensional hypercube. Okay, then if we use two of these one-dimensional hypercube, for example, this 0, 0 and 0, 1, and another one we call it 1, 0 and 1, 1. Okay, then the corresponding pair of nodes, for example 0, 0 and 1, 0, you make a connection, and 0, 1 and 1, 1, we make another connection. Okay? Then it becomes something like this. Okay, and this is a 2D hypercube. Okay, again you can construct a 3D hypercube by two of these 2D hypercube. Okay, and for example, you one of them you give another binary. For example, we call it 0 2D hypercube, and another one is 1 hypercube. Okay, then we have something like this. Okay, this one is 0 hypercube, and 2D hypercube, and the one behind is another hypercube. Okay, they work as one. Okay, then we connect corresponding nodes. Okay, because each two-dimensional hypercube has 4 nodes, so we have another 4 connections for this 2D hypercube. Okay, then we create a 3D hypercube. Okay, and formally you can define this by another way to define a hypercube. For example, because it's a K-array, right? K-array, and K is binary. Okay, so for example, if you are n node, that means you have log n dimension, okay? And every dimension you only have 2 values, 0 and 1. Okay? That's binary means. Okay, and so every node in this n-node hypercube can be represented by a vector of log to n values, and every value will be 0 or 1 or in every dimension. Okay. And then n log n dimension hypercube will be something like that for any two nodes if their coordinate, okay, differ in space. Only one place, okay, only one bit. For example, when the level of this one is 1, 0, 0. So all the nodes they differ with this one. Their levels only in one bit. But first word, the difference in first bit will be this node. So you have a connection. The second bit difference will be this one. Okay, so 1, 1, 0. These two nodes differ in the second bit, and the last bit difference will be this one. It's 1, 0, 1. Okay, something like that. So another definition is you can connect and log n dimension hypercube by this way also. Okay, and for this kind of structure, okay, the diameter will be log to n, and average distance again is in the order of the log n, and actually it's 1/2 of log n. Okay, and bisection width is in order of n. Okay, and constant will be 1/2 also. Okay, so to separate this to two parts, remember this was created by two of these. Okay. So to separate them, the best simplest way is we just remove those links, we'll connect two of 2D together, okay? And then that's for node we have four 2D is 4 nodes, okay? And when you go to the 3D it's 8 nodes. Okay? And that's we need actual 4 links. Okay? So if we remove those 4 links, then this degrade to two of this 2D, right? And this 2D hypercube are disjoint, and their size will be the same. Okay? So that's the definition of bisection width. Again, so it's half. Well, and 4D hypercube you can connect by two of these 3D and connect the corresponding nodes together. Okay? That's direct interconnection network. That means every node has computing power and the networking capability together. Okay? But if the system contains two kinds of nodes, one is network node, another is computing node. Okay, so and their functionality are different. The network node only deal with networking, they relay the messaging, they route the messaging, and the processing node they have computing power. Okay, for this kind of system or network, we call it indirect interconnection network. For example, bus is the typical one. Okay, this here, the bus is the preload of the networking node. Okay, it only relay the messages. Okay, all the messages go through this shared bus. Okay, and computing node, these other nodes connect to this bus are the computing nodes. So Ethernet can be created like a bus or hardware. Okay, it's conceptually similar. Okay, but implementation may be different. Okay, and this kind of system, the diameter will be 2 because you go to the network node and then go to from the network to another computing node. So the longest distance between any two nodes will be 2 halves. Okay? Again, the distance is also 2, and cost will be constant because as long as the bus you have enough the connector here, then you can increase the number of nodes connected to the same bus, okay, without too much cost. So the cost can be treated as a constant because the cost of this hub or this bus is almost independent to the number of computing nodes connected to it. Yeah. And another type of this indirect interconnection layer is crossbar. Okay, we mentioned that in previous lectures. Okay, here this crossbar are network nodes. Okay, they only doing the relay of the message. Okay, they don't have the computing power. So only the nodes connect to this in the boundary have the computing power. So, okay, again, it is an indirect network. Next, very commonly used topology is tree. Okay, and if we organize a tree as a two-dimension planar tree, okay, so you don't have any close layer, okay, and then it is a hierarchical topology, okay, and a node have some channels and so on. Okay. So in tree topology, usually these intermediate nodes, okay, they only play the role of the network. Okay, so the message only goes through these intermediate nodes, and the computing nodes usually they are organized in the leaf. Okay. So any two computing nodes they try to communicate with each other. They will send message up to the same common center. Okay. Then down. For example, this H1 want to communicate with H4, then the message will go up to the same ancestor, and then go down to M. And for a binary tree architecture, the messaging, the longest space for this kind of messaging passing mechanism will be 2 times the height of this tree. Okay? And the height of the tree usually is in the order of log n, and is the number of leaf nodes, okay? And so on. So you can see that this distance will be log n, in the order of log n also. So from the point of view of distance, average distance, it's good. Okay? And the diameter is also in the order of log n. Okay? But the disadvantage is that the bisection width usually is 1. Okay? Because if we remove these two links, then the system becomes 2 independent disjoint trees. Okay? Parts. We remove these 2 links, or even remove 1 link. This part and this part, they become disjoint, and the size of these 2 parts will be almost equal. Only the difference is 1. Yeah, so the bisection width is 1. That means with only 1 single link failure, it's possible the system become 2 disjoint parts, and they cannot communicate with each other. Okay? So the fault tolerance of this kind of mechanism usually will be concerned for the design. Okay? If you design the system like this way. Okay? So the upper layer is switching node, but and the nodes in here are the processing nodes. And because a lot of traffic goes through this, especially, for example, this half, the nodes in this half, if they want to communicate with nodes in this half, they all need to go to the root node and then go down, right? So the bandwidth or the traffic of the root node become highly, it's a hotspot, okay? So the traffic pattern for this is hotspot, it's not uniform, right? And this one, may become the performance bottleneck because a lot of traffic goes through route. Okay, and also and the bandwidth requirement for this one usually is higher than the other nodes. So there's a variation of this kind of tree, of a binary tree. We call it fate tree, okay, to avoid this bottleneck problem. Okay, we make this communication nodes, okay, with bandwidth, different kind of bandwidth. For example, if a single line will represent 1 unit of bandwidth, okay, then here because for this switching node, only these two nodes will go through this one to communicate with each other, and then the other traffic they all need to go up, okay, and the traffic may come from this both of these, so we give double bandwidth capacity for this connection and so on. So you double the bandwidth capacity for every layer up, okay. Then the performance wise, okay, not the photon wise, not the fading reliability, okay, the performance wise. Then if even this one is the bottleneck, it require a lot of traffic goes through there. But because the bandwidth capacity of this one is much larger than the other, so the performance wise that would be tolerable, would be acceptable, okay. But again, the bisection width is still one, okay, it's still one in some sense. But if physically this 4 line is not conceptual, but physically you put 4 connected line there, then the photon of this node, the system will also go up. Then because now you will have a connection for this node, right? Instead of 2. Right? So you remove one link, the system is still connected. Yeah. So by doing this phase tree design, okay, not only you satisfy the bandwidth requirement, you let the hotspot become the load of this one that can be spread by these different links. Okay. And also by adding these physical lines, okay, not the bigger these physical lines, they are independent. Okay, so the fading of these lines or links should be independent. Okay, then the photoness of this one is also increased. Okay, so that's why if you like this tree type of connection, then this fade tree probably was better than normal binary tree, okay, in most cases. And thus, section we discussed this multi-stage interconnection in some part, okay? But we did not go to too much detail. Here we will give more detail about this multi-stage interconnection network. Okay. We can the reason for this or the philosophy behind this is that a big crossbar will require a lot of space. Okay, so by using this multi-stage interconnection, then it can probably reduce the memory requirement or space requirement. Okay, and this interstage connection can be connected by different kind of permutation function. Okay. And here we were talking about some of these very famous or commonly used permutation functions. Okay. So in general, this multi-stage interconnection can be conducted by interconnect an input to an output with k by k crossbars. Okay. And every k by k, okay, and there are log k of n stages. Okay, with each stage has n over k these crossbars. Okay, and here in most cases this k will be 2. Okay, depends on what's the building block of this crossbar. 2 by 2 crossbar is the most fundamental building block. Okay, but if you like 4 by 4 or your IP, then 4 by 4 will be alright. Okay, or even other kind of K. Okay, but most cases we use 2 by 2. Okay, and so the total number of links will be something like this. Okay. Here is a typical example of this omega network. Okay. And the connections are all connected by perfect shuffle patterns. Okay. Here, the shuffle means if we shuffle this, then it will be something like this. You separate this by okay. You like you shuffle cards. Okay. You cut this to 2 discs, and then you shuffle them together. So the distribution will be something like this. Is a new distribution will be something like this. Okay. So this link represents a perfect shuffle. Okay. Operation. Okay. And omega is connected. For example, is a 16 pole or 16 input omega network. Then you require 4 stages. Okay. And every stage you have this a 2 by 2 crossbars. Okay. Here we use 2 by 2 as our building block. Okay. Then this is a perfect shuffle. Okay. Also, and of course the last stage is a direct link to the output. Okay. And the routing for this one is very usually simple. Depends on the destination node. Okay, or the address of the destination node. Okay, for example, if this one 000 try to send message to 100. Okay, so it will go up. Okay, in the first bit is up, and then the other 3 bits are 0, and if we 0 means go down, then you go down, and here go down to here, then go down to here, then go down. No, so it's in reverse order. Let's see. This one. Okay. So 1 is down, 0 is up. Okay. 1, 0, 0. Okay. Here. And the last one is 0 also. So there's a 2 link out. Okay. So the logic is something like this. Use the address of the bit pattern of the destinators. Okay. And 0 means you 1 means down. Okay. 1 use the downlink, the output downlink. 0 means you use the output uplink, and then you can this simple routing strategy is possible to route the message from the source to its destination. Okay. Another kind of connection or patterns can be used to construct this we call it baseline means. Okay. The first stage is a perfect shuffle, and then the second and the other stage they are inverse shuffles. Okay, but in different way. Okay, the second one is the whole set n by n inverse shuffle. The third stage become half. Okay, so you have 2 inverse shuffles, and each is the half size of original. Okay, and then the later stages, you reduce the size to half also. Okay, so the inverse. So in here you have 4 by 4 inverse shuffle, and this is another 4 by 4 inverse shuffle. So the last stage it becomes a 2x2 inverse shuffle, okay, and so on. So that's the baseline network. The capability of this multi-stage network, for example, is omega and baseline, are almost same, okay? But the purpose are different because by using different kind of connection, you may achieve some specific purpose. Okay? But most of their capability are almost identical. Okay? Another famous one is butterfly, because it looks like a butterfly. It's a crossover. Okay, here. Okay, you see. The first one is a direct link. Okay, and then second stage is a 2x2 crossover like this, and then third stage is a 4x4 crossover, and then a bigger crossover. Okay. So shuffle and here and inverse shuffle and crossover are three most commonly used permutation patterns. Okay, and you can combine these together and then you construct your own network with some specific characteristic and so on. Okay. So here's another example called cube. Okay. The first stage is perfect shuffle, and then use crossover. Okay. And the crossover is from the big to small. Okay. The first one is second stage n by n, and then you n over 2 by n over 2, and reduce by half for each stage and so on. Okay. And this one we call cube network. Okay. In general, this multi-stage network are broken network. Yeah, for example, because the definition of broken and non-broken here is that if two messages they send from two center and their packet are different, okay, then they should not conflict with each other. Okay. This kind of network we call it non-broken. Okay. And close by is a typical example. As long as two different center they try to send message to different target, then they will never conflict with each other. Okay, right, close by. However, for this omega or the other cube or baseline or whatever, they are in general are broken because, for example, for this 4 try to send to 0, and 0 try to send to something. It may not try to send to 0, but if you try to send somewhere, okay, for example, they need to go through this outer link, okay, and then maybe go down. For example, 0 try to send to 2, it should go through this link, right? And this one will be conflict point. Okay? Although the message came from 2 different sender and target to 2 different receiver, but they still may conflict in some intermediate stages. Okay, and so in general, this kind of network are broken. Okay, because that they may conflict with some other traffic, although their target may not be the same. Yeah. To make multi-stage network become non-broken, okay, one clever design is this closed network. Okay. They use more stages to make this conflict become eliminable, become non-broken. Okay. So, for example, this n by n close is a 3-stage. Okay. The first one, first stage is something you have two by two crossbar in here, and then direct link to the original input. And this crossbar link to two n over 2 by n over 2 crossbars. Okay. So this is a two big crossbar. Okay. Depends on number of n. For example, n is 16, then this one is a by a. Okay. So half of n by half of n. So we have two of this. Okay. And then and this is an inverse shuffle. Okay, from this first stage to this second stage. Okay. So second stage has a two big crossbar. Okay. And then third stage is a perfect shuffle, go out. Okay. Something like this. Because this crossbar is non-broken, right? So by using these two big crossbar in the middle, okay, it's possible this network will become non-broken. Okay. The reason for non-broken is that because there exist alternate paths between any two nodes. Okay. For example, the node 0 try to send message to node to here, node 1, for example. Okay. In Omega, for example, if node 0 tries to send message to node 1, then it should go through some. Let me see. 0, 0, 1. This one is 0, 3 stage, 0, 0, 1. What's 1? 0, go up, and then 1. Okay, so go down, something like this. Okay. But there's only one path for any source and destination. There's only one path. Okay? There's no other way between this node 0 to node 1. The only path is something like this. Okay? So that's why the routing is simple. Okay? Very straightforward. Okay? But here, for 0 to node 1, you can go through this crossbar by take the first output link, go to this third stage, and then take the down link out. Right? That's one way to do that. Okay. Another way to do that is that you use down link, go to this down crossbar, and then use this upper output, go to this, and then use the down link. So you have two alternate paths between any two pair of nodes. So to make this system conflict-free, they all not working in long time. That means the decision, the routing decision must very clever, such that the message sent out from these senders. They need to go to some place, make a global optimal solution, the routing decision, and then different messages. They find out a good routing strategy such that they will not conflict with each other, because every two nodes has two different paths. Then you just allocate those paths in such a way that they will not conflict. Okay. So for this kind of non-broken multi-stage networks, okay, the routing become not straightforward. Okay. There's no straightforward routing mechanism, because the routing depends on the message, the destination, the distribution of the destination and the centers. Of course, we only allow, for example, here is 16 nodes connected by this one. So we only allow 16 messages sent out, right? Because any node can only send out one message at a time. For example, okay, there's a basic assumption like this. Okay? And so you have 16 traffic exists, and as
as long as they all target to different destinator, okay, then you always can find a routing strategy such that these 16 messages can be delivered without any conflict. But to find out this routing for any pattern, okay, any input pattern, is not a straightforward task. Okay, give you as an exercise if you are interested. Okay, but it's a good exercise to try to develop an algorithm. Okay, for this kind of. And if you are interested and you cannot find out the solution by yourself, you can always find out from the internet. Okay? There's a lot of past work and discussion, something like this. Okay? But because this is half n over 2 by n over 2 close bar, right? So the size space is still almost n squared, right? So, but the capability of this 3-stage closed network is become equivalent to a closed bar, right? Remember, a closed bar, you can simultaneously schedule n messages, right, from the source to destination, as long as the target are all different, right? So their capability is equivalent to n by n closed bar. Okay? But instead of using a big n by n, use a little bit smaller, okay, n half by n half, 2 of this, okay? And the space of this is a half of n by n, right? The space requirement is something like that. So remember, this is equivalent to n by n closed bar, right? And here we have a n half by n half closed bar. So again, we can replace this closed bar by a smaller closed network, right? So by these 3 stages, the first stage is this one, inverse shuffle, second, the last stage is perfect shuffle, and then we are in the middle, you have 2 4x4 closed bar, right? You can always replace a bigger closed bar by something like this, right? And recursively apply this mechanism, you can make closed bar then eventually the closed bar is 2x2 closed bar, right? So eventually you can construct something like this. It's non-broken, right? Only by 2x2 closed bar. Okay? And that's something like this. Okay, we replace this one by a smaller, okay, 3-stage closed. Okay? And this kind of recursive application, okay, they have another term we call it Venice network. Okay. So this is a 16-pole 5-stage closed network. Okay. And then we can apply the same mechanism recursive to these 4 2x2. Okay. And then it becomes something like this. Okay. So eventually all the switching unit are 2x2 closed bar, right? And the non-blocking property is still preserved. Okay? The only drawback is that the size become almost twice as normal multi-stage network. Okay? Almost twice, and not twice, okay, but almost twice. Okay? Because the stage number is 2 times log n, okay, minus 1, something like this. And the original is log n stages, and here is 2 times log n minus 1. for this 16 node beneath, okay, so and everybody only 2 by 2 are used. Okay. Then any 2 nodes, any 2 pair of nodes will have A alternate passes. Okay. So you can see the routing strategy become even harder. Right? The original close we only had 2 alternate passes, right? Because one goes through the upper half crossbar, and another one goes through the down half crossbar. Okay. But here, because we reduce the crossbar ultimately every crossbar is 2 by 2. Then we have 8 different alternate passes. So every pair of node they have 8 different hops. And whenever you have a 16 message comes in input, then you find out, you will schedule this stuff. So this everybody will not conflict with each other. Become not a trivial task. Okay? So any 2 node, but you always can find out 8 different places. Yeah. So close and beneath are non-blocking. Okay, it's easy to show. Okay, the reason for the non-blocking because they have alternate passes. Okay. And because the 3 stage is non-blocking, so we replace the recursive. So all the beneath are non-blocking. Okay. The problem is the size become almost twice. The network we are discussing is the topology, okay, for how to place those network nodes and computing nodes. Okay. Now we are thinking how the messages are really delivered. Okay. Besides the routing, you also need to deliver the message, right? After you decide how to the message should go through which path, okay? But eventually you need to deliver the message, okay? And the message delivery, usually you have 2 mechanisms. One is circuit switching, another one is we call it packet switching. Okay, the concepts are a little bit different. Okay, if the messaging, okay, the whole messaging, okay, is a communication unit. Okay, from the application point of view, okay, we try to send something from a host to another host. Okay, and those something, the size of the something may be varied because for different purposes in different time, they will be different. Okay, and in general, the size will be restricted only by the memory, the host, the memory size, okay, for each host. And packet usually means a fixed size, the smallest unit of communication. Okay, message is the application point of view. Okay, you try to send something from A to B. Okay, those the something depends on the application. It depends on the time. Will be different, right? Okay, the only constraint will be the memory size. Okay? As long as the memory is big enough, then it should be able to contain any size of the message sent. The packet usually means the fixed size unit which are used to send through the underlying network. Okay. Okay. Most networking, okay, underlying the physical network, okay, they have limitation how each time how many bits can be delivered for every instance, okay, of a message transmission. And those usually means that they should be, the size should be fixed. Okay, so the bandwidth, the physical bandwidth network management will become much easier because physical bandwidth management usually consider a lot of time. Okay? most common way right now is by using time division. So you separate time to small units, and every small unit you let some message go through, okay, and so on. So the time, and during this small time interval, how many bits can be delivered? It depends on your communication mechanism. Okay, more advanced, you maybe can transmit more bits during that small time windows and so on. Okay, but however, usually these time windows are limited. Okay, in some sense. So the size during that particular time interval should be limited also. Okay, so that would restrict the size of this packet. Okay, usually. Okay. So packet usually the size of packet usually depends on the underlying networking technique, physical network technique. Okay, which kind of network you are used. For example, in Ethernet, the messaging, the packet maybe 1.5K or whatever, something like this. Okay, and for different kind of physical network, for example, the GSM may be different. Okay, and 5G they may be different. Okay, but however, this difference limit the size, okay, of the package. So every time when you deliver, you have a limited size, and we call it the communication units. Okay, and then the packet usually named as this fixed size communication unit can be used delivered on the line. Okay, and usually this packet contains some routing information because the design of this physical network usually they try to make this design is routing independent. Okay, so any kind of routing mechanism may be able to use on top of this physical network. Okay, so usually they will reserve some place that routing information can be put in there, and for some error control or flow control purpose, usually you have a sequence information put in there also. Okay, let's take a short break. Okay, real quick. The packet usually contains this routing information and sequencing information. The purpose is that for different routing mechanism, they may use different, they may need this information. Okay, so usually a packet will contain a part we call it header. Okay, and inside there you can store this information. Okay? And the size usually is in the in this hundred of bytes or thousands of bytes, okay, of a packet. Okay. So message may be participant to fix size the packet, okay, and every time it deliver is by packet. Underlying physical network deliver transmit by packet, okay, and packet usually contain some headers, okay, and usually most of the time the header will contain destination information, sequence number information, and so on. Okay, and then followed by some data, and this header and data. Okay, so a packet may be separated to smaller units. We call it fleet. Okay, and some of fleet may belong to header. Some of fleet are data. Okay, and some system they may even participate this free to fit. Okay, but here in most cases, free is small enough. Okay, for the management purpose. And the underlying delivery, okay, or the routing strategy. Okay, they use these two kind of mechanism. One is circuit switching mechanism. Okay, circuit means you connect two points together, okay, and make electronic circuit. Okay, so the electronic signal or voltage current can go through one end to another way. Okay, so that's the circuit. Okay, and circuit switching means whenever you try to send message, you create a real circuit, okay, electronic circuit from the sender to the destinator, and after this circuit created, then the message delivered from one end sent through this circuit to the other way. That's the name of the circuit switching. Okay. So communication between the source and net has two phases: circuit establishment and message transmission. So before you send real message, you need to establish circuit first. And this circuit is a physical path from source to destination, and reserved by the circuit establishment mechanism. Yeah. In general, the way to establish circuit is that sender may send routing related control information. Sometimes we call it routing port, okay, which contain the address of destination and some other routing or control related information, okay, to the destination. Okay, but in this probing part, the depends on the routing mechanism. Okay, one possible way is you just send this probe to every outgoing links. Okay, all possible outgoing links from this particular node. You send out, and any of the receiver, after receive, they try to find out a way to the destination. Okay, if it's possible from there to the destination, then it can probe again, send out a probe again. Okay. So this kind of mechanism sometimes we call it flooding mechanism. So you just propagate all these requests like flooding, okay, like water flooding. So you from source and then all the connector, all link are flooded by this probe. Okay, and eventually one of the probe will reach the destination fast enough, okay, or earliest probe reach the destination. Then the path from the source to the probe will be selected as as a circuit, okay, for the real message. The others, they eventually will die out, okay, because eventually those may also come to the destination also, but the destinator will know that, okay, it already see the plot, okay, so it's not the first plot from the center for the particular purpose, then it just delete, okay, and so this kind of broadcasting mechanism or throttling mechanism may generate a lot of prop traffic, okay. So usually they are used when you don't know the network, okay. You have knowledge about how the network connected, okay, in the beginning, so you can use this kind of mechanism. Okay. But if in most cases, when the network was built, only in the beginning phases you need to do this something like this. After a while, you will have every node will have some knowledge about the network. Okay, so in general, this routing plot will be more target oriented. Okay, so the sender it will not flop all the plot from all the outward neck. It may select one or two possible route, okay, based on its current knowledge about the network. So the prompt machine may send out from one or two outward links, okay, it's all. And this information, control information, will tell the receiving switch how to continue to propagate this prompt and so on. So reduce the traffic generated by this routing plot. Okay. So different routing mechanisms, they may use different way to avoid to generate this problem flow. Okay, and eventually one of the prompt messages will reach the destinator. Okay, and depends on how you do the prompt. Okay, it will have two mechanisms, two general mechanisms to reserve the circuit. One is the problem. When the problem goes through, then the pace deliver the probe to the destinator will become the circuit. Okay, and so usually for this kind of mechanism, okay, probe reserve phase link when you transmit through that. The reason to do that is that the routing is decided from the center. Then you can do that. Okay. Otherwise, you don't know this probe can succeed or not, right? So if the probability goes through one week, then you make a reservation. If eventually the probability cannot go through to the destinator, right? Then they need to revoke those reserved links. Okay? You need to do that. Okay? So another way is that if you are not 100% sure this problem goes through this particular pace, can reach the destination, then that's another way. Okay? The reservation is done by acknowledgement. When the problem can arrive to the destination, destination will send back acknowledgement through this arriving paces. And during this egg pace delivery, the acknowledgement reserve those links. So when the acknowledgement came back to the source, the link also reserved. Okay. Okay. So that you have two kind of mechanisms to reserve this circuit. Okay. One is when you send out probe, you reserve the circuit in the same time. But the problem for that is that the problem may be unsuccessful, may fail. Then you need to revoke those reserved links. Okay. So another possible way is by using acknowledgement. Okay. When probe go to the destination, and then the egg goes through in the reverse order to back to the source, and during this acknowledgement delivery, they also reserve the pace. Okay. So when you receive the egg, sender will transmit the whole message through this reserved circuit. Okay. And the pace will release. Okay. Again, this release pace it can have two ways. Okay. One is after destination receive, then send out a revoke message to release all these reserved egg, or you can during the message delivery. Okay. Once the message is sent out of particular reserved link, then you immediately revoke. Okay. The reason we have these two options is that the first option is much safe, because if during some in the middle transmissions something happens, right? You need to do some retransmission or whatever. Okay, so then it's possible. Okay, because you still the link is still there, right? But if you immediately remove, then sometimes if it's not goes through, although the link is reserved. Remember, anything can be failed, okay? In any time, so it's possible after reserve during the transmission, some link block, and if you remove those delivery link, then some message may lost, right, during the transmission, because you trust me, and then you release the link, but however the message is not delivered, then you may need to retransmit, and you find out the link is already released, okay, and so on. So and also it's possible the failure is not happen in the link, it's happen in the intermediate switches, right? You reserve a link from one intermediate node to another, right? And the link between them. So send up during the transmission, some intermediate node A will send out a message, and then it expect the B will receive, right? But after send, it drop the link. But however, because the B somehow failed during the transmission, and then the message lost, right? If you did not have some safeguard. So the second approach may be much safe. So you until the destination receive the message, you make sure the message is delivered to the destination, and then destinator send back to release those reserved channels. Okay, so that's two options. Either way is possible. Okay, depends on how the design strategy or how confident you have for the system. Okay. Okay, so the conceptually is something like this. Okay, in the A part, there is a probe message or the probe gate to the destinator. Okay, and eventually when the probe message come to the destination, the egg will send back, and during the egg reservation is also done. Okay, and the last stage, the message will go follow this reserved circuit. Transmitted from source to the destination. Okay. Another way of the messaging is we call it packet switching. Okay. So instead of we reserve a whole path or whole circuit before sending the message, okay, you did not do any resource reservation. Okay. You store and forward. Okay. You send messaging to the next possible intermediate node. And after those nodes receive the whole message, the node now it's responsibility to forward the message to the destinator. Okay? So that's why we call it store and forward packet switching. Okay? But because for the purpose of the managing the network related resource, so usually you will not try to store and forward the whole message. Okay? Because the whole message may be too big and the size is very, okay? So it's difficult to manage dynamic or variable size mechanism. Okay, anything is variable will make the management effort become much complex. So to make management or buffer management become much simple and easy. So usually we need to have a fixed size, okay, mechanism. So packet is a fixed size mechanism. So, okay. So message will participate divided into fixed size packet, and every packet delivered on your own, okay, individually, and follow this store and forward concept. Okay, from the center is try to send to a particular intermediate node, and hope that node eventually can forward message to the packet. Okay. So message is split into packets, and packet, of course, we said contain some fleets. Okay, some of them are header, some of data. Okay, and here we assume every channel has input and output buffers. Okay, input buffer can store message comes in. Output buffer used to store message, waiting for the communicated output links. Okay, and the size of each buffer, we need to be big enough to contain the whole packet. Okay, packets are delivered individually from source through intermediate switches. And also some assumptions that the whole packet maybe need to be copied from output buffer of the current switch to the input buffer of the next switch. Okay, that means the message is delivered from one node to another node. Okay, and then store there. So finish this store and forward. Okay, and routing decision will be made by each intermediate node, okay, based on the information contained in the header. Yeah. Okay. So that's the basic requirement for the store and forward packet switching. And conceptually, something like this. For example, this is the messaging, a packet. Okay, and these are fleets. Okay, different color means different fleets. Okay, the first one usually are the header fleet. Okay, so routing decision, when this comes in, the decision will made in the first switch will decide which output link should be used to forward this packet. Okay, so for example, select this output link, then the message, the packet will be copied to this output buffer. Okay, and the size of the buffer can contain at least one whole packet. Right, and then because this output buffer corresponding to one particular output link and to one particular intermediate switch. Okay, so the content of the here will eventually deliver to the input buffer of the next switch. That's all. Okay, and then in here this switch will decide which output link it should be take. Okay, to forward to the next switch. Okay. So before that, you need to copy this one to this output buffer, and then when the link, physical link becomes available, then it will deliver this to the next switch. Okay, so store forward is something like this. Okay, so eventually it will come to destination, and then we go on. Okay, to the computing nodes. So you can see that by doing this, okay, depends on how many intermediate switches the packet will go through. Okay, the timing requirement to deliver a packet from source to destination is depends on those switches. Okay, and the traffic pattern or the load of those switches. Okay? They all affect the real the actual latency of this message, this packet delivery. Okay, and because the decision for a switch to make, they need to wait until the whole packet is in its input buffer. then you will examine the header and make the decision to. Okay, for example, you should go through this output link, okay, and copy this packet from this input buffer to its particular output buffer, okay, and so on. Okay. So a variation of this store forward mechanism, sometimes we call it this cut-through packet switching. Okay, will be that because the whole packet contain the first free comes in is the header free, right? So as long as the header free is in buffer, the decision should be able to make. Okay. So cut through means you try to make decision as early as possible. So when the header is already in input buffer, then the decision can be taken and immediately decide, okay, this output link should be used. And then, so the data movement, data copy is not whole packet, essentially inside a switch, okay, from its input buffer to a particular output buffer. This data copy is not done by the whole packet, but done by free, okay. So whenever the header free comes, it's already in there, and then you can make decision. So you can start to move the header free to the header free of its corresponding output buffer. And when the next free comes in, you just move, okay, accordingly. So it's more like a pipeline mechanism for the data movement. Okay? Instead of you wait everything comes in and make decision, move the whole block. So whenever you can make decision, then you start to move. Okay? So when a new free comes in, you immediately, because you already know this particular packet, the data free of this particular should go to which output buffers. Okay, so you just make immediate data copy. Okay, so you don't need to wait until the whole packet. So the best principle is this. Okay, because packet they have some header free and data free. Okay. So the incoming header free can be cut through to the next switch. But not next way, but the next output buffer. Okay, and when the header is in the output buffer, and then if the corresponding output link becomes free, then the header can start to be delivered. Also, you don't need to wait the whole packet in the output buffer. So as long as you decide which output link should be used, so the header move to the output buffer. And then, if the corresponding output link become free, then the header should be able to start to deliver to the next switch input buffer, okay, and so on. So that's the route we call it cut through. Means you try to go ahead as soon as possible, okay, whenever you already make decision, and whenever the corresponding resource is already there, then you just do it. You don't need to wait. Okay, so that's the concept. Okay. So every further free buffer and also cut through to the next switch. Okay. If the output is free. Okay. Now if in some switch the header cannot proceed, that means its corresponding output link is not available, then header will store in its input, in its output buffer, right? And wait until the whole packet comes in, okay? And until the corresponding output link becomes free, then you start to go through this cut through again. Okay? So that's the purpose of that. So you deliver the freeze as soon as possible. Okay? But whenever you need to wait, then you wait. Okay? So the advantage of this cut through is that the worst case is the performance will be same as the store and forward. Okay, but in most cases it can be a little bit better, okay, than the pure store and forward. Okay. That's why it's worth to discuss this. Okay. So if there's no contention, that means all the corresponding link variable. Then it's like a pipe line. Okay, every you free by fleet. Okay, the message delivery is one fleet at a time, and then they just go through like a pipe. Okay. So conceptually something like this. Okay, when the first header comes in, then you can make decision. Okay, so the header can deliver to the next switch immediately. Okay, so if this the link is free, and so on. So this the deliver is become free base. Okay, not packet base. Okay, you don't need to store the whole packet and deliver the whole thing. So you can, whenever a free is coming, you can deliver immediately. Okay? So it's something like this. So when this header comes in here, or if the decision can be made, so this output link should be chosen. So you can immediately put in here, put it, and then if this link become free, then it should go away. Go until somewhere, for example, here you have a output link is occupied by other message. Then this header free will stop there, waiting until this one become free. Okay. So eventually this one free, then we can immediately go through. Okay. And so on. So let's cut through packet switching. It still is a packet switching, but it's a special design. So you don't need to wait a whole packet. More, okay. The cut through, and the only difference between cut through and the pure store forward is that the message can be the header or the free data free can move much quicker than the whole package. Okay. But the buffer size for each input one is still, because the worst case is here, because sometimes you stop here, then you need to have a place to hold the whole packet, right? So every input buffer and output buffer, they need to have at least can contain one whole packet. Okay, that requirement is the same. Okay, but later some design they try to reduce this buffer size. Okay, because here the delivery is in free, right? So as long as header free is in, then you can make decision and so on. Okay, so this we call it one-hole packet switching. The basic mechanism is same as cut through. The difference is that now instead of every input buffer and output buffer has big enough to contain one packet, they only ask to contain one free is maybe enough. Okay, but there has some disadvantage for that. Okay, so let's see the packet. Because packets split into fleets, okay, and there's sneaks through. Okay. So the performance will be same when there's no conflict. Okay, free can go on one at a time. The difference is that they don't need to hold the whole packet; they only hold fleets. Okay, one or more, few fleets. Okay. Again, the header free view the whole page. And the sequence of buffers and so on. Okay. But the problem, because the buffer may not be able to contain a whole packet. So a packet may split into different switches. And in the middle, some switches may store one free, two free, and the other. So the whole packet may be split into several switches. It's like a snake, right? Your snake head already in there, but the snake body is still left behind somewhere, okay? Something like that. Yeah. Okay. So here in the extreme case, if the every buffer only have big enough to contain one free, then things will be something like this. Header, and then if your header can move on, then you move on. Okay. But here, if the header cannot move up, then the whole packet will be split into several switches, okay, like a snake body. A snake head here, or snake body is still there. Okay, it's all. Okay. So because this a packet may occupy several switches, right? And it's not a good thing because the resource of this links or these channels are all busy by this particular packet, right? If the packet cannot go ahead, and then you take all the resource, okay, and this resource cannot be used by other messages and so on. Okay. So usually this kind of case are more proper for the system which is the traffic is not too high. Then the opportunity of this happens will be low. Okay? Then it's not a big problem. Okay? But you get the advantage of that. You use a smaller size of buffers. Okay? But later this design is not attractive anymore because buffer is too cheap right now. Okay? So nobody cares about the size of the buffer anymore. Okay? So the package switching, pure packages, pure store and forward or this cut through become much often commonly used. And this wormhole only discussed in literature. Nobody will try to use this kind of case anymore because buffer is too cheap. Okay? It's nonsense to use this smaller buffer anymore because it costs almost ignorable. So okay, that's why we only discuss. Nobody use this kind of mechanism at all. Okay? But wormhole is still useful because it's possible you can get a better performance. Okay? Okay. For this network behavior or capability could be, then the system of every switching node or a node in the directed network will contain a network capability. In general, we need to have a network interface board in each node, okay, or in the switching node. Okay. So all of these computers, they need to have some interface to network, okay, to connect to this interconnection network. And usually this network board will contain its own random access memory, okay, for buffering purpose. Okay. And they may have one or more DMA channels, so you can move data from the node, from the storage or secondary storage of the computer node to the network board. Okay. And so on. And sometimes you have a spatial computing power or computing chip processing node, processing unit in this network board also. Okay. So and this network processor, okay, sometimes we call it network CPU, okay, NPU, okay, it's used to offload some functionality, okay, for CPU. For example, for this signal processing mechanism, okay, or for doing encryption, or doing compression, or transmission management, and so on. Okay. So a network board may contain some processing unit, so they can deal with this network. So the main CPU is doing the computing. Okay. The network board, the CPU or the processor in the network board is doing some network purpose operations. Because in multi-computer system, okay, every computer is its own, right? And there's no physical share the memory, right? So you can only communicate with each other by using messaging, okay? Send out message. So message copy become the important issue. Okay? How many messages need to be copied from one place to others? Okay, that's all. In general, a message inside a computer, okay, with this network boards, okay, they may take this action. For example, a message first move to the buffer of the center's network board from the center's computer, the memory, or from the center's disk, right? Depends on where the source, the message are stored. Okay. And then move to close this network, right, to the receiver's buffer, right? But during this copy, okay, from computing nodes memory to network board's buffer, okay, you may do one copy or two copies, depends on what kind of mechanism are used. Okay? Because if the system use the messaging is not stored in kernel space, but in user space. Okay? Some system, whenever you doing the network, you need to copy from user space to kernel space to system's buffer, and then from system to network's buffer, right? So you need to do two copies. Okay? Even from the application's user space to its own network buffer. You first from user space to kernel, and then kernel space to network board. Okay? That's two copies. Okay? To avoid these extra copies, some mechanism may be used. For example, you can treat this network board, the buffer in the network board, as a kernel space management by the operating system directly. Then it's possible you copy to kernel, actually to the particular network board. Okay. That's one possibility. Okay. Another possibility is that when you're doing the networking, you don't need to copy the data from the user space to kernel. Okay. You can set the user space data become accessible to the kernel or accessible by this DMA in the network board. So the DMA in the network can move the whole buffer, whole data from user space to its network board. Okay. So you have these two approach at least, okay, to reduce the actual copies, okay, between these buffers. Okay. Or another way is like here, you map the network board's buffer to user space. But usually it's not recommended. Okay, you map this one to kernel space is much meaningful. Okay, but direct to the user space, okay, you increase the lot of management effort for that. Okay. Or some systems use this two network boards for each computer to reduce data copy. One for operating system, another one for user process. Okay. So making this to network board, so network board's buffer can be allocated to user space directly, but that board is used by user space. Kernel use another network board. Okay, that's another way. Okay. So you will not have any conflict between user and the operating system. Okay. But anyway, this the purpose for this is try to reduce the actual copy from user's memory to the network board. Okay. You try to make this copy only one copy. Okay, instead of two or more copies. Okay, so in general, without any specific spatial consideration or setup, okay, in general, the copy is you need to copy data from user to operation and then to network board and then go through switch to the buffer of the receiver and then go to the receiver's kernel and eventually go to receiver's application. Okay. So that's very common. You have this 5 data copies. Okay, if only go through one switch. Okay, but if you need to go through several switches, then you need to have more data copies. Okay. And inside this network board, okay, they may have some CPU or processing unit in there also to take care of the network purpose. Okay. And some network board, okay, they support multiple queues. Okay. Instead of using multiple board, okay, you can have a single board, but because the reason for that is that the memory is so cheap, so you can have a lot of buffer inside the board. And how to utilize this buffer more efficiently. This multi-queue mechanism was proposed. It's very similar to cache line, okay? But now the buffer association of the buffer is not the memory but the process. Okay, you can use process ID. For example, the last few bits or the first few bits of the process ID. For example, if you have 4 queues, and so you use 2 bits of the process ID as the hash, right? So you have 4 queues. So for example, you use last 2 bits, then last 2 bits 0, 0. Then you always the data you want to send out, you always go to the first queue, the 0, 0 queue. Okay. If your PID process ID the last 2 bits is 0, 1, then you always go to 0, 1. For example, something like this. Yeah. Process ID is another, and if you instead of process ID, another possibility is the section number, okay, or the transport ID, okay, because network, especially in internet, if you're using the TCP/IP network suite, then transport ID may be possible. Okay, a different transport, you can go to different queues. Okay, and so on. The reason for that is that then the buffer assignment, buffer allocation becomes easy because whenever you know the message you want to send out from one particular channel, one particular PID or particular transport, they always go to that particular queues. Okay, that's for the output buffer. For input buffer, you will do similar allocation also. Okay, input to particular transport, they always go to particular queues. Okay, then the management become much easier. Okay, that's the reason, because the buffer is too cheap right now, so you can have a lot of buffer space. But so it's possible you can separate this buffer into different queues instead of using single queue. Okay. One example is this one. Okay. Intel one i350. Okay, you have a lot of input buffer and output buffer together. Okay. So the base, it's like this affinity. So sometimes we call it core affinity. Okay. Yeah. And this association is it can based on the TCP flow. That means you use the transport ID. Okay. Or maybe use the usually they use TCP which queue the message should go to, and so on. Now we understand this physical network and the mechanism, okay, either circuit switch or flag switch. Okay. Now let's discuss the mechanism may be used for application. Okay. A typical message operation or something like this, send and receive, right? It's most common interfaces. Okay. In general, when you need to send something out, you specify the destination ID. In any way, ID means a way to name the destinator, right? And with a pointer, the address, starting address of the message, and so on. Okay. And when receiving when you try to receive, you make also similar interfaces. Okay, specify which sender's message you want to receive. Okay. And with a reserved buffer, so the incoming message will put in there. And so on. That's a very common or general purpose interface for the send and receive. To implement this or provide these operations, okay, the semantic for this send and receive may be different. Different systems they may provide different semantic. Okay, and the major difference would be this blocking semantics. Okay, so the call for send and receive is broken or not. So that means blocking means if for some reason this operation cannot take place immediately. For example, you don't have buffer, or your network is not ready, or whatever reasons, right? This send cannot immediately carry or receive, cannot immediately perform because no message there for you to receive. Okay, and so the sender or receiver may need to be hold temporarily, and then until the corresponding resource become available, then this operation can be performed. Okay. So that's the blocking. Okay. The caller may be blocked until the message can be sent. Okay. The caller of the receive may be blocked until the desired message arrives. Right? The reason for this blocking may be different. Okay. But somehow the interface need to specify when or how this behavior, how the system will behave when the operation cannot be performed immediately. Okay. Here we discuss send first. Okay, so if in the non-blocking and blocking mechanism for the send. For blocking send, that means you send running and then stop somewhere. The message waiting for the message to be sent. Okay, and here before this message delivery actually complete. Okay, for any reason, okay, maybe you need the delay or the latency of this actual send take place and complete may be dynamic barrier. Okay, so eventually when this message sent, then the sender unblock and continue. Okay, let's stop here. We will discuss in next week.
就是你如果把那所有的 buffer 啊，把它 map 成kernel OS 直接把它 buffer，所以你的 copy 就直接 copy 到这里，不要 copy 到那里。所以就少了这一步到这一步，就直接它 copy 到这里。那这是一种做法，就你直接让它让